This is lesson 2 of unit 2 on derivatives. So this lesson is about tangent lines and the derivatives. So we are going to be connecting what we did in lesson 1 to a more formal introduction of the derivative. So in calculus, we have two big problems that we deal with, and they are the tangent line problem, which is about instantaneous rate of change, and that's where our derivative comes from, and the area problem, which are known as integrals, and we'll get into those in chapter 5, and they are finding area under curves. So with both of those, how we go about coming up with a method for solving them is we set up a limit, and we're going to be using limits throughout this course. So from the previous lesson, we talked about the difference quotient, and we found a general slope formula, and we could find the slope of the tangent line at any point provided the limit existed. So this general slope formula, as we're calling it now, is in fact the derivative. So this general slope formula is our derivative. And what's read f prime of x, and if a function that has a derivative point is said to be differentiable at that point, and that word's going to come into play quite a bit as we move forward. All right, so the official definition of the derivative. The derivative of function f with respect to x is the function f prime whose value of x is given by this formula. M, which is the slope, is equal to f prime of x, and that is found by taking the limit of our difference quotient. The limit as h approaches 0 of f of x plus h minus f of x over h, provided the limit exists. Now I have a little note here. The domain of f prime consists of all of the x values in the domain of f of x where the limit exists. It could be smaller than the domain of f because it's possible there are points in the domain of f where there is no derivative. So if f prime of x exists, we say that f is differentiable at that point. Differentiable at that point. Okay, so here's how the notation looks. There are different ways to write the derivative, and I know this can be a little confusing, but this has to do with the fact that this concept was developed pretty much independently on two different land masses. One was the British Isles with Newton, and the other was in the German Republic with a mathematician called Leibniz. So both notations have survived to this day. So if we write f prime of x, like the first one, it's very formal. We know the name of the function because we could have g prime of x, q prime of x, and it also tells you what the independent variable is. Using just y prime, it's shorthand, brief, and but you don't know, is t the independent variable, x, what is going on? Usually we use that when we're doing x and y, but it's like a shorthand notation. And then we go to the German notations that were developed, dy dx, or you can say the derivative of y with respect to x, and we use the d to show we're taking a derivative, and we use the y and the x to show both the dependent and independent variables. Dx, or the derivative of f with respect to x, it's similar to dy dx, but now we have the function's name, and it may seem awkward, but once you use it for a while, it becomes very familiar. And then finally, this is the very formal one, d dx of f of x. Or we're actually showing, look, we're going to take the derivative of f at x, and it's showing exactly what you're going to be doing. So that's the different ways you're going to see notation for the derivative, but they all mean the same thing. You're going to be taking the derivative, which means you are finding the slope of the tangent line, or the limit of the difference quotient, which leaves us to different ways we represent the derivative. Graphically, what you're looking for is the slope of the tangent line. So it's the slope of the tangent line at a specific point P. Okay, numerically, the derivative is the limit of the slopes of the secant line or the limit of the difference quotient. And verbally, what you're saying is that f is differentiable at a point. If and only if, that's very important, it has a defined slope at x equals a. It says, use the limit process of the derivative to find the general formula dy dx for the derivative f of x equals 2x squared minus 3x. So we are finding dy dx, because that's the notation they want us to use in this problem, which means that we are finding the limit of the difference quotient of f of x plus h minus f of x all over h. Because we weren't given a specific point, so we're going to just find a general formula, as it says in the directions. So substituting in, I'm going to take the limit as h approaches 0, and I'm going to substitute x plus h in my function, and I'm going to have 2 times x plus h squared minus 3 times x plus h. That's the first part of the difference quotient minus the function f of x, so that's 2x squared minus 3x, and this is all divided by h. And now it's just a matter of doing some algebraic manipulation. So we're going to take the limit as h approaches 0 of 2 times x squared plus 2xh plus h squared minus 3x minus 3h minus 2x squared plus 3x, and that's all over h. So one more step to start simplifying things. I can at least get rid of the 3 x's. They are opposites. Remember what we said from lesson 1, that if the derivative does exist, all the terms that have no h will be eliminated, because then we will have a limit. So what do I have left here? Minus 3h minus 2x squared, and this whole thing's over h. Now the nice thing is I can eliminate the 2x squareds, and I get very happy at this point because I no longer have any terms that don't have h in them. So I have 4xh plus 2h squared minus 3h over h. So a factor of h will go away, so my denominator goes away. So I have the limit as x approaches 0 of 4x plus 2h minus 3. Substituting 0 in for h, this term goes away. So my dy dx becomes 4x minus 3. So that's our first example. Okay, now example 2, we're given y equals x squared minus x. Use the definition of the derivative again to find f prime of x. So what we have is that f prime of x is the same as saying y prime, and we're going to use the definition of the derivative. So we're going to do the limit as h approaches 0 of x plus h minus f of x all over h. So this is going to equal the limit as h approaches 0. I'm going to substitute now. X plus h squared minus x plus h. That's the first part of the limit. Minus, and I'm going to substitute in f of x, which is x squared minus x. And this is all divided by h. Okay. Doing a little algebraic manipulation again. You get x squared plus 2xh plus h squared minus x minus h minus x squared plus x all over h. Now here right away we can see our canceling. We have a positive x squared and a negative x squared. We have a minus h and a plus h. I'm sorry, minus x and a plus x. So our limit simplifies to 2xh plus h squared minus h all over h. And again, a factor of h will be canceled out. So I'm left with the limit of 2x plus h minus 1. Now I can substitute, and that h goes to 0. So I get that f prime of x is going to equal 2x minus 1. Okay, I'm going to stop this video here, and then I'll continue in the next video.